guys, today we will predict customer churn in telecom industry. Now, in telecom industry, customers are able to choose from multiple service providers and they can actively switch from one operator to another. Like for example, if you decide to switch to a different network today, you just have to visit the store, you have to fill a form maybe, and it will happen very seamlessly. So that is the reason the telecom operators are so much worried to retain their customers. The customers they already have, they don't want to lose their customers because it's quite costly to get new customers. So that is our goal today, to understand and to try to predict the customers who are most likely to churn or who are most likely to leave for a better service provider. So, as we can see, the telecom industry experiences an average of 15 to 25% annual churn rate. Given the fact that it costs 5 to 10 times more to acquire a new customer than to retain an existing one, customer retention has now become even more important than customer acquisition. So that is our main goal here. We are only bothered about the existing customers. We are not going to be thinking about new customers here. And for many operators, retaining high profitable customers are number one business goal. To reduce customer churn, telecom companies need to predict which customers are in high risk of churn. So as data scientists, our goal will be to do that for the telecom industry or for a particular telecom company. In this project, you will analyze customer level data of a leading telecom firm. Of course, we are not given the name of that firm. Build a predictive model to identify customers at high risk of churn and identify the main indicators of churn. So not only we are going to build a model for predicting churn, we also need to understand what are the main driving factors or what are some important features by looking at which we can say that these are the main driving factors for customer churn. So now I will move on to the approach. Basically, before starting the full analysis process, I jot down a simple list of things I'm gonna do, and sometimes I just make few changes here and there once the complete thing is done. So this is the final approach in nutshell. So I'll just go through it very quickly and then we will move on to the coding part. So first and foremost, of course, we have to import the data from the comma separated file, and then we will prepare the data. We have to filter the high value customers. So we actually got a really big data set which has information about a lot of customers, but since business can take care of only a particular group of customers that are the most important or the customers who bring the most of the revenue to the company, we will only be focusing to those customers or the high value customers. Then we'll do a few more data preparation steps like dropping features with no variance or deriving new features, labeling churn status, because the data set we will look into in a few minutes that this doesn't really have any target variable in it. So we have to decide like what is churned or what is non-churned. And then we have to deal with missing values. We have to deal with outliers if there is any. We have to check for correlation. Then we will also do bivariate and multivariate analysis. We then split the data in training and test set. We will do feature scaling, and we will also check for data imbalance, because in such scenarios where we are dealing with churn, most of the customers will not churn. So there will be a very few percentage of the total customer that are gonna churn. So that should not affect the quality of our prediction, right? So we have to take care of that. Then we are going to make a predictor model, where we will be only worried about how accurate our prediction is, and then we will also make an interpretable model which will be helping us to understand what are the important features driving the customer churn, and we will also give some business recommendation. So now moving on to the coding part. First of all, here I have imported all the necessary libraries. I kept all the things at the top of my code. Some people usually do it in the middle section, wherever they're using something they're importing it, but I prefer it keeping at the top, which makes it even cleaner. And it is also useful when suppose there is any change in the model name. Sometimes the libraries changes and you have to change in the code. So basically you don't have to go through the complete code. You can just come here, see the first few lines, and you can easily change it from here and move on with your life. So yeah, first we have taken the data into a pandas data frame, and I have set index mobile number because mobile number is an unique identifier which can identify each customer uniquely. That's why I have taken mobile number as the index. Next, we are checking for the numeric and categorical features. Looks like we have a lot of features here. And look at that, we have 99,999 rows of data and 225 features. Can you imagine? Now, if we have this much of data, my laptop is definitely not gonna take it. And also, for the problem statement, it was made really very clear. If you go through my GitHub, the original very detailed problem statement, you will find all the things I have done, like why I have done. You have to go through the detailed problem statement here to understand the reason. In the blog, I have just mentioned in short what is the main goal for the data scientist to do, but if you want the complete picture, you have to go through the version I have uploaded in GitHub. So first, we are filtering the high value customers because those are the people we will be focusing on today. And how we are going to do it, this is already mentioned in the problem statement, that you can take the 70th percentile of average recharge amount for the first 2 months good phase. So one more thing that I should mention here at this point, that this particular data set or the data frame, pandas data frame we are dealing with right now, this has 4 months data. Okay, this has 4 months data, 6, 7, 8 and 9. So the first 2 months, 6 and 7, I can quickly come here and show you from here. The good phase, the first 2 months will be considered as good phase, where the customer is happy and behaves as usual. There is no change in behavior. And then is action phase. This will be our month number 8 in the data set. Action phase is when the customer is like, there is some visible change in customers' behavior. Maybe they are recharging less this time, or maybe the monthly usage have decreased a little bit. So those will be the indicators clearly visible in action phase, or month number 8 in our case. And churn phase is when the customer has already churned, or customer stopped using the telecom, service of the telecom operator. So month number 9 in our data set will be the churn phase. So this data we cannot really use it. We'll just decide the churn level because the target variable is not given in the final data set. So we'll just decide that from this, and rest of the things we will just remove. And for the action phase and good phase, we are going to take a very good look at. Next, So we are filtering the high value customers as given the definition in the original problem statement, which is like who have a recharge of equal or more than 70th percentile of average recharge amount of the first 2 months or the good phase. So basically for doing that, I'm just taking the average recharge amount of 6th and 7th month, and I'm just checking the describe. Basically it looks almost the same. Then I'm treating the missing values here before taking the average, because otherwise it will create a problem. If there is any null value in one column after average, we'll end up getting null value in the final column as well. So we don't want such scenarios. That's why I am doing a missing value imputation just for these two particular features. Then I have taken the conditions and I'm checking how many rows are matching for those conditions, and ultimately we are getting around 30,000 rows for high value customers. So these 30,000, almost 30,000 customers will be our main focus here. Now we'll go ahead with the data preparation phase. First, the thing I did is deleting some of the features, dropping some of the features which has no variance whatsoever. So for that I just did a value count, and since these are categorical variables, it will be really very easy for me to do. And for numerical variables as well, if it has single value or value count is giving 1, means it has no variance. So if it doesn't have any variance, it cannot decide how the variance is changing for target variables. So best thing to do is just drop those features. That's what I did here. This is the list of features which has no variance at all, so I have dropped them. Next is deriving new features. Now the data set we got, the features that we got in hand are not really very useful if we don't derive new information from them. They're not very useful to use directly. So we are gonna extract new features and we will use them instead of the original features. That's what I'm doing here. So recharge related, first of all, there are a couple of columns with recharge related data. Like there are recharge data, we can see 3, right? And there are recharge. So this is for data recharge, the people who use mobile data, and this is for normal like talk time recharge, or like the people who recharge all together. So those two. So first of all, we will be working with the recharge related data. So basically here we are dealing with the dates, and as you can see we are only working with the good phase and the action phase. And for good phase and action phase we are given the last date of recharge. This is the last date of recharge for data, and this is the last date of recharge in general. It can be same or it can be different, but this has to be the general one. So I think the data recharge is the subset of the general recharge. That's what I can think about. And this date is given. So if you think about feeding this date directly to the machine learning model, it cannot really make sense of it, make sense out of this. Also, there are a lot of missing values in these features. As you can see, these are missing values. 6,000 missing values are there for this. So what I did here is, instead of having 3 different last date of recharge for 3 months, for general and for data 3 again, so total 6, I will be having 2 extracted features. Let me explain that further to you. So I will be having something as last date of recharge. See here, date of last recharge and date of last recharge data. So I'll be having two new features. And how I'll get this one? The date of last recharge is nothing but the most recent date of recharge among 6th, 7th and 8th month. So we'll start from 8th month. If the data is available for 8th month, then that is the most recent, right? So that date will be assigned to date of last recharge. If we have missing data in 8th month, then we will check in 6th, then we'll check in 7th, because 7th is the immediate previous one. So we'll check in 7th. If 7th is still present and 8th is not present, then 7th we can consider as the last when the customer recharged. And if 7th is also missing, then we will check in 6th month. So if there is any recharge done in 6th month, so we'll just assign that date of 6th month as in date of last recharge. And same thing we are doing for recharge data as well. The logic is same. Now after getting the two dates, like what is the last recharge for general and what is the last recharge for data, what we are doing, we will be counting the number of days since the last recharge was done, because again we cannot work with this date time index or this date time object directly. Because of that, I will be converting them into number of days, which will be just like integers. So we can feed it into any kind of a machine learning model, right? So here I have taken a reference date of 1st September, because we are working with only the data of 6th, 7th and 8th, which is June, July and August. So I am assuming that this data will be available to me by 1st September, or the first date of the churn phase. And then I am calculating the difference. Basically, with respect to 1st September, how many days have passed since the last recharge has been done by the particular customer. So that is what I am doing. I have taken the recharge stat here, and I am just deducting the date, and from that I will get the number of days since last recharge. So from that I will be getting plain integer numbers. So first we had so many dates, and now we have number of days since last recharge was done. So yeah, basically after all these things we have done, now we don't have any missing values, and we have very useful data, and which will come back later. Now I am dropping the original date features. Next thing that I have did is 6th and 7th month. So basically there are some features available for 6th, 7th, 8th and 9th month. So I'm just checking if the features are same or there are some extra features for any particular month. As you can see, the features ending with _6 and the features ending with _7 I am checking here, and both are 49 as we can see. So it means we have the similar things like ARPU, these things. For comparing the data of good phase, that is 6th and 7th, with action phase, that is month A, taking the average usage of 6th and 7th month and deducting usage from 8th month. Positive value of derived feature would mean usage has dropped from good phase to action phase. That is, average usage of 6th and 7th month is greater than usage of 8th month. Negative value means usage has increased in action phase, and features starting with derived underscore prefix in their names are derived as mentioned above. So what does this really mean? Here, instead of taking 6 and 7 months and 8 months separately, we are deriving a comparative feature. So if the feature has positive value means basically the derived feature is a comparative value. It is not the actual value. So it will only tell us how much the usage has increased or decreased in action phase in comparison to good phase. That is what we want, and from that only we are going to decide how the customer is behaving. Is the customer's behavior suspicious in any way, and definitely that will help us to understand whether they are going to churn or not. So that's what I did here. Basically there are a lot of features, 49 features as you can see. So for these 49 features we'll take average for the first 2 months and then we will deduct it and we'll get the comparative value. Next we have to label the churn status. Since we haven't got the churned value already in our dataset, we have to obtain that in some way, and this is already given in the problem statement. Then that look at these features, if there are 0 values for each of these features means the customer has been churned. So that's what I did here. This is already mentioned here. You can go back and look at this. So for churn customer, we are considering that total incoming monthly usage, total outgoing monthly usage for month 9 are 0, and volume 2G in MB, volume 3G in MB are 0. Basically it means that there has been no incoming or outgoing calls and there is no data usage for 3G and 2G in month 9. So if there is no call usage and there is no data usage by the customer in month 9, then we are considering that customer as churn customer, and that's what we are doing. We are just checking the conditions, and if all the conditions are true, then we are labeling as churned. If not, we are labeling as unchurned. As you can see here, we have 2,567 customers, high value customers who churned with respect to the definition given in the problem statement, and there are 27,811 customers who did not churn. And also we have the similar features available in month 9, but we don't really need those, because in this phase we don't need these things. We can only use the first 3 months data, and suppose we are doing this on the first week of the churn phase, and as soon as we get the data, as soon as we get the results, like these are the customers, we'll just go back quickly to the sales team and ask them to do whatever to retain these customers. So that is the whole idea. We'll be dropping all these features. This is what is mentioned in the original problem statement as well, to drop all the features having _9 at the end. So this is the high value customers, and after dropping all the rows, dropping all the features of month 9 and also deriving the new features, we have 57 features. This is the new dataset. Okay, as you can see, there are still some features that slipped out of our observations, so we'll deal with them now. We're just checking them, what is there. and dropping the redundant features. Here again, these will be redundant because once we derive the features, because this was left out because first we did with _6 and _7. That's why this was not captured in that logic. That's why it's always a good idea to go back and check the like new data frame so that you don't really leave out any feature. Okay, I think this case study is going to take a lot of time for me to explain. Anyway, I'll try to like speed up a little bit, but here it is. We are just doing the same thing, taking the average and deducting month number 8 value from that, getting the comparative value, and then just dropping all the original features. Next thing we are doing is missing value treatment. As you can see, first I am checking for all the features having more than 40% missing values. So I got some of the features which has like 0.5, 0.5, that is 50% missing values are there. So this is quite alarming. If we decide to keep this data, this is going to badly impact our machine learning models performance. That's why this will be wise to drop all these features having 50% missing values. Okay, next after dropping all this, next I am checking what are the features having less than 40%. So first I checked very high percentage of missing values, so we can just drop the features. We're not going to do missing value imputation for them. And for the features having comparatively lesser missing values, missing value imputation is possible. So that's what I'm gonna do here. As you can see here, 8%, most of the features have 8% missing value, and one has 33% as well. So how should we do the missing value imputation? Because for deciding that, I have checked the distribution of these features. As you can see, all these features are numeric now, so we can easily check the distribution here. As you can see, some of the features are a little bit skewed. So for the skewed features, it's a good idea to impute them with mode value. So that's what I did here. I imputed all these features. This is already taken in a list, so I'm just particularly considering those features having missing values and imputing them with most frequent value or mode, and checking the data frame again, because sometimes some mistake can happen and we can miss out something, so it's a good idea to check back. As you can see, all are coming as 0, means there are no missing values at all. Next, I'm doing outlier treatment. There are a lot of features, so it's a good idea to like club some of the features together and see the box plots, even though you cannot really see the exact level for all of them because some of the features are in different scales. Because of that, it's not really visible for all the features, but it's a fair idea. It gives a fair idea that some of the features have quite a lot of outliers, and this is gonna impact our final model. So this is the first set, this is the second set, this is the third set of features we checked. We could have taken all the features together as well, but visually it will not be really very appealing and it will not be really very helpful. So it's better to like divide the data in small sections, small segments to visualize when we are dealing with a large amount of data, a large amount of features. So here I have just dropped and kept the values, basically taking the lower whisker and upper whisker as the minimum and the maximum permissible value, and any value which is lower than that or higher than that will be made equal to the whisker value. Basically, that's what I have done here. Q1 is the 25th quantile or the first quartile, and Q3 is the third quartile or 75th quantile value, and the interquartile difference is the difference between these two. This is the interquartile range actually. So this is the difference between the 75th and 25th quantile. We can get here, as you can see in the box plot. You can see from here. So we are just considering this whisker and this whisker. Any value on top of this will be reduced to this whisker, and any value below the lower whisker will be increased through the lower whisker. That's what I did here for all the features, and now after that I am checking for correlation of the features. And as you can see, there are some features now after dealing with the outliers having constant values. Since they are having constant values, there is no variance, and hence no correlation has been seen so far for those features. So we can just safely drop those features. That's what I did. After outlier treatment, some features have no variance, identifying those features have fixed values in all rows and removing them. That's what I did. Next thing, bivariate and multivariate analysis. This is always an interesting thing to do. First I took derived total recharge amount and derived total recharge number. Total recharge number is nothing but how many times the customer recharged in a month, and derived means basically that taking average and deducting the value of month 8 or action phrase from it. So it will give the comparative data for amount and number. Also, this is important to look at the features. They are not taken very randomly. By reading it, you can understand that there should be some relation between the recharge amount and the number of recharges done. So that's why I have taken this two in particular for plotting this graph. And as you can see, for non-churned and churned, we are seeing here, and this is the positive part and this is the negative part. And yes, so positive correlation is there, of course, between the recharge amount and number of recharges. So the features that I took here are definitely not taken randomly. You can always check the meaning of the features and try to understand which features will make sense to take together, things like that. And then derived features, I'm again explaining how this has been derived. So a positive value of this feature means recharge amount value dropped from good phase to action phase, which can be alarming. And same applies for recharge number. So recharge number positive means there is a drop in action phase in recharge number. A negative value is actually good. Negative value means the recharge amount value has increased from good phase to action phase. So those are the good customers. They are not gonna churn. They are enjoying the service, so we'll not be bothered about them. By comparing churned and non-churned, as you can see here, this is more confined in this area, which is this positive, and this is positive as well, which means that for the churned customers, both recharge number of recharge amount have dropped in action phase, which makes complete sense, isn't it? Next, I have taken derived last day recharge amount and derived maximum recharge amount. For that as well, we can see that here the concentration is more for churned, like both are positive. This also means that for churned customer, it is more likely to have a drop in last recharge amount and maximum recharge amount. So that is one of the visible change in customers' action to decide who is gonna churn. That's what I explained here in the comment. Next, we have plotted for number of days since last recharge and last recharge data. This is basically a discrete variable, so cannot really see like this one. As the plot was not really helpful for concluding anything, I did some further calculations here. I checked how many percentage of people have recharged when. So from that we can see something useful. Okay, the above two features extracted by counting the number of days between the last recharge date available, which I already explained. By comparing churned and non-churned customers, the customers who have not recharged in 17 days or more are highly likely to churn. About 32% of the churned customers did their last recharge 17 days ago. On the other hand, 8% of the non-churned customers did their last recharge 17 days ago from the reference date of 1st September. This is our assumption. This we take for our ease of like calculation, but we could have taken any other date as well. Number of days since last recharge is likely to be low for non-churned customers. Means, as you can see here, 16% customers which are retained have done recharge just 1 day back, or just 2 days back 13% of them recharged, or 3 days back 10% has recharged. So that's what I'm saying, that they are more likely to recharge recently than the churned customers. Next, I have taken few more features here, like derived this is STD, incoming, monthly usage, local outgoing monthly usage, average recharge amount. So these features are not showing much strong trend, except for this one. No conclusive trend visible for churned and non-churned customers for these above features. As you can see here, not really anything visible, right? Then what we are doing is splitting the data into test and training set, because of course we want to have a part of the data which is unseen to our training model, and then we will evaluate our model based on the performance on the unseen data. Next, I have done the feature scaling. Feature scaling is important because, as we saw in the outlier treatment, before outlier treatment, when we plotted the box plots, we saw that every feature is not showing very clearly because the scales are so random and so like different. Because of that, our model performance will be impacted as well. So we squeezed everything down in a fixed scale with standard scaling. Next, we are dealing with data imbalance. We did a sampling here. I did SMOT here. So this means first we had, as you can see, 24,000, almost 24,000 entries for training, and of course in that again the churned customer percentage will be very less. We did the data imbalance treatment so that our training model gets a good look at the churned customers, because since the original data set had so less percentage of churned customers, we are sampling the data in such a way that there are more representation of the churned customer level. So for building the predictor model, where predicting churn is more important than model interpretability, dimensionality reduction technique PCA, or principal component analysis, has been used for independent variables. And for identifying most significant driving factors for customer churn, we will not use PCA because PCA is what will make us lose the interpretability of the model. So first we have built the predictor model. The predictive model will be using the principal components, right? So first, this is some reusable code. I will get back to this later. First, I have made the logistic regression model, and again for the PCA part, I have taken 10, 15, 20, 25, 30. So 5 different principal component numbers, and we will see that on which component number the base model is performing the best, and depending on that we will decide the number of principal components. And since we are using logistic regression model as our base machine learning model, we also have to deal with the different values of cutoffs because that will decide the model accuracy and other things. So since we have 2 different parameters to consider here, I have built 2 different data frame. One is for accuracy test data and the other one is for sensitivity test data. You could have used training data as well, but definitely it will be a little bit misleading because the model is more likely to perform better on the training data than test data, but test data will tell us the original performance of the model. So it's always good to have the test performance. So that's what I did. Basically, I took the components, principal components. First time I took 10 principal components. I built a logistic regression model and I calculate the sensitivity and accuracy, and next I built with 15 components. I calculated the same, and so forth for up to 30 components. And also I have calculated the metrics for different values of the cutoffs. So as you can see, we got the 2 data frames, and as after inspecting the accuracy and sensitivity score, we are going with 15 components and cutoff 4, as you can see here, these 2 values. So this is basically a little more than 70% for the accuracy, and sensitivity is quite good here. If we take this one, say for example, if we take 0.3 for cutoff, then we are getting very less accuracy. This is a decent accuracy and the sensitivity is quite fine. So that's why I went with this cutoff and this component. So we will be using 15 principal components for rest of the classifier models as well. The other classifier models that I have built here are decision tree, random forest, and XGBoost. So that's what I did here. And for decision tree, random forest, and XGBoost, I will just explain one, and similarly I built the others as well. So since we can do some hyperparameter tuning for all these classifications model, right? That's why first I did a grid search cross validation, and there I fed all the hyperparameter tuning I want to do for say for example decision tree classifier. Here I gave the maximum depth, mean sample lift criteria, all these things, and from that I got the best estimator, best params and best estimator, and from that I built the decision tree. And with that best decision tree obtained from the grid search CV, I got the model performance. Say for example, for decision tree, as you can see, the accuracy and sensitivity score are there. Same thing I did for random forest and XGBoost. So first feeding the grid search model with a list of parameters that I want to check, like what is the permutation combination which will work best for my random forest classifier model. And once I get the best estimator, I just check the performance on test data, and this is what the result is. Next I did for XGBoost the same thing. Now one question here, like why I just took this 3 value and not more. This is only because I had computational limitations. I was using Google Colab, and it was taking quite a lot of time to like run this grid search CV. The complete code that I am walking you through now took around 45 minutes to like run completely. That's why there was a lot of restraint for that. Because of that, I just kept it really short. If you have more resources than I had, you can definitely make this list even longer, and you can try other combinations as well. But since I tried multiple times, I just used different combinations, and whatever I found to be well suited, I just kept it for my final notebook. So finally, we have the list of evaluation matrices for logistic regression, decision tree, random forest, and XGBoost. And as you can see, by comparing the accuracy and sensitivity score on the test data of different models, we can see logistic regression has the highest sensitivity score and lowest accuracy score. But here, for this particular case study, we are more focused on the sensitivity than accuracy, because sensitivity is the measure, like how much percentage of the churned customers we are able to predict, and accuracy is something like how much of our predictions have been accurate among the total predictions. So it's okay if we predict some of the unchurned customers as churned customers. That's not the problem. But we want to predict, or we want to capture as much churned customers as possible through our machine learning model. That's why we are more inclined towards the sensitivity score than the accuracy one. That's why we have chosen here the logistic regression model. As you can see, with cutoff point 4 and 15 principal components, we could achieve sensitivity score of 0.83, means 83% of the churned customers have been predicted correctly by our predictor model. So that's what. So I am just building the final model, and here, since we did for 0.4 and 15 principal components, now I am just digging a little bit deeper and trying to understand if we can like optimize it a little bit further, like if we can change the cutoff a little bit and make it even better from there. So that's what I did after just taking 0.5, 0.25, 26, 27. So for 0.01, every 0.01 I have checked for range 0.25 to 0.49, because we already took around 0.4, right? So I'm just taking around 0.4 in even a smaller interface. And as we can see here, 0.42 is even better for a logistic regression predictor model. Next, we have to build up interpretable model. So the most challenging part is already over. This one is going to be super easy. First of all, this is a feature selection model we have to build. This has to be like interpretable, which will be helping us to like recommend anything for the business. So first I did is Using RFE, I just got 20 features to start with, and then first I got the 20 features. Then I will be building logistic regression model, and I'll be inspecting the variance inflation factor and the p-values respectively, and I'll be reducing, or I'll be dropping the features one by one. So first, to begin with, I selected 20 features automatically by RFE, and then say we got top 20 here, right? And then I'm just looking at the variance inflation factors for the top 20 features. As you can see, the first feature has VIF of 10.04, which is quite a large value for VIF. So we'll be dropping that. We have to go one by one. So that's how I did here. First one is dropped. So we have top 19. Build the model. Checking the VIF. Again, dropping the highest VIF. Building the model. Next, VIF is looking kinda decent, but p-value is going wild now. So dropping the feature with highest p-value, which is again more than significance value, which is 0.05 we assumed for this case study. Again, we are checking. P-values are fine. VIF is still more than 2.5, so we'll be dropping that. We have top 15 features now. As you can see, we have VIF quite fine. P-values are looking good as well. So we have top 15 features now, and this is the correlation metrics. As you can see, there is not much of a correlation present in the features right now, which is a really good thing. And next thing, I just build a random forest classifier to get the feature importance. Random forest classifier has a feature importance attribute, this one, feature underscore importances underscore. So this attribute is giving a numeric value, importance of each feature. So this is the list, final list of top 15 features, which is also asked in the problem statement. And next, we are checking for all those important features again, taking a deeper look. As you can see here, number of days since last recharge and last recharge data. I am checking for non-churned and churned customers. And I am also checking some numbers. And yeah, so for churned customers, average, okay, I'll go back to this. For the churn customers, average derived local incoming equal to 13. This means why I'm checking these values, and I'm just explaining what this means. So those people whose minute of usage of incoming calls from other mobile means this T2M. This is actually different combinations like same telecom operator or different telecom operator, or same telecom operator, fixed phone or mobile. There are so many combinations present in the original dataset. So no need to bother about that. Just try to understand the basic thing, which is the people for whom the minute of usage of incoming calls from other mobile dropped by 13 units in action phase are likely to churn. Means basically that usage has dropped in action phase. The value of derived local IC T2T MOU can be interpreted similarly, means dropped in action phase will signify chance of churn. For churned or non-churned derived local outgoing telecom operator to fixed monthly usage unit average value is similar. So we cannot really conclude anything significant from that. Next we have derived last recharge amount is obtained by subtracting the large recharge amount of action phase from average. That is how we derived all the features. Higher positive value means greater drop in the recharge amount in action phase, and if there is a significant drop of last recharge amount in action phase, then good phase, that definitely signifies a chance that the customer is going to churn. Next we have ARPU, derived ARPU, which is I think average revenue per usage or per user. It's obtained by, again, same thing, taking the average and deducting the value of 8th month. Higher positive value means drop in revenue in action phase. If there is significant drop, means customer is likely to churn. Then we have AON is nothing but age of network, means for how long the customer is using this network. Relatively new customers are more likely to churn. As you can see here in the box plot, this is a little bit in the lower side, and the customers who are retaining, like these are the loyal customers, they have been using for so long that there are less chance for them to like really leave the telecom operator for something else. Also, I derived some values here. Negative value of derived total recharge number means increase in total recharge number in action phase. For retained customers, there are a lot of customers for whom total recharge number increased. And positive value means, of course, about 12% of churned customers total number recharge dropped by 10 in action phase. Say for example, suppose I used to, this number may sound insane, but say for example I used to recharge 15 times, okay, 15 times on average in a month, and suddenly my average number of recharge became 5. So according to this observation, since my average number of recharge dropped by 10, means I am more likely to churn. So we are just getting some values which will indicate high probability of churn. Derived feature gives a comparative measurement. So fraction is also acceptable, negative, positive, all values are acceptable because we are just comparing action phase with good phase. Positive value of derived max recharge amount and derived average amount data indicate that drop in maximum recharge amount and maximum recharge data in action phase. Of course, because the usage is dropping, means the customer is definitely going to leave the telecom operator for something else. So these are the recommendations. I'll just read it out. Conclusion. Okay, all right, I just explained the technical terms. Now I will explain in business terms, nothing technical here. Okay, so I gave almost 10 business recommendations based on my observations. So I'll go through one by one. First of all, customers with number of days since last recharge 17 or more are most likely to churn. Sales team may focus on customers who have not made a recharge in last 17 days or more. So if we are getting the data by the beginning of the month, we can definitely ask the sales team to check if the last date of recharge is 17 days old or more, then these customers should be focused, should be considered first. Then we have number of days since last recharge data. This is also same. If they recharged almost 1.5 months ago or even more than that, then these customers are more likely to churn. Then we have derived local incoming calls. Drop in incoming calls also can signify possible churn. So we should give them, if this is very old data, I think this is couple of years older because there is no 4G and 5G usage available, so only 2G and 3G is there. So basically it is possible that at that time the telecom operators used to charge customers for even incoming calls. So I suggested that the incoming call charge can be reduced, or there can be other possibilities, like the places where the network quality is quite poor. Things like that can happen. So if the customers are moving in such areas, then the incoming calls can be less. So we have to take care of both the network service and also how we are charging the customers. Excuse me. Next we have high positive value of last recharge amount. Means since this is the derived feature, and high positive value means a huge drop in the amount, huge drop in the value in action phase. And we have also come up with the value of 35. If it is more or equal to 35, means the customers are going to churn. So drop in large recharge amount in action phase is an indicator of churn, is an important indicator of churn. Next we have customer with high positive value in derived ARPU, which is the average revenue per usage. So if the average revenue is derived average revenue is positive and high, means 160 or more, since it is a derived feature and this positive high value means there is a huge drop in the average revenue in action phase, means these customers are definitely going to churn. So we should give them suitable offers which can be used by the customers. So if the customers are more of mobile data users, which we can definitely understand by looking at the other features like mobile data and talk times, so minute of usage. From that we can decide like which features, which offers will be more suitable to them, and we can give them those offers. Next we have age of network. Again, customers which have age of network less than 800, means customers who are using the network for more than for less than 2 years. So it's like from a month to almost 2 years. Within 2 years, the customers are more likely to churn. After 2 years, the customers are more considered as loyal customers, as we saw in the graphs as well. And then we have positive value of derived total number of recharge. If it is more than 10, means if it is dropping by 10, means high chance of churn. Positive value of derived maximum recharge amount and derived average recharge amount data indicate drop in maximum recharge amount and recharge data in action phase, which in turn indicates high probability of customer churn. And last but not the least, we have derived volume. 3G MB means for churn customers. Huge drop in 3G data usage in action phase for customers who churned. Telecom company may need to revise its 3G data plans in order to retain customers in 3G using 3G data. So there can be a possibility that other competitive telecom operators are offering more attractive 3G data options than this particular operator. So maybe because of that, maybe the customers who used to use 3G data are more likely to churn because of the like difference in the charge, difference in the price. So that can be one more important thing the telecom operator can think about. And so yeah, that's it for the case study. In conclusion, we can say that these are the business recommendations we can come up with from our analysis. And for the final predictor model, we have a logistic regression model with which we derive 82% of the sensitivity, means 82% of the churn customers have been predicted correctly by the model. And this is, of course, we are talking about the model performance on unseen data. If we had considered training data performance, it would have been much better, but we are taking the performance on unseen data, so this is the correct thing to do. And also we got accuracy score of 0.74, means 74% predictions made by the predictive model are exact or accurate. And the interpretable model has top 15 features, and these are the features. I already explained each one of these features and how they are affecting the churn. So that's it for the case study. I hope you liked this case study. Let me know in the comments below what you liked, what you didn't like, and if you have any further questions, you can always ask me in the comments below. I will get back to them as soon as I can. And leave a like, share, subscribe. That's it for today. Bye guys.